Wide area monitoring, protection and control. Wampac represents a paradigm shift in power system operation, enabling system-wide visibility and coordinated control across vast geographical areas. Traditional power system monitoring and control have been limited to local measurements and regional control centers, leading to blind spots in system-wide dynamics. Wampac addresses these limitations through synchronized measurement technology that provides a coherent, time-aligned view of the entire power system. The growing complexity of modern power systems, driven by renewable integration, market liberalization, and increasing interconnections, has exposed the limitations of traditional approaches. Major blackouts worldwide have highlighted the need for better system-wide visibility and coordinated control mechanisms. Wampac systems provide the infrastructure needed to prevent cascading failures and enhance system reliability. The key objectives of Wampac include enhancing system-wide visibility through synchronized measurements, enabling real-time monitoring of system dynamics, implementing coordinated protection schemes, developing adaptive control strategies, improving system resilience to disturbances. Synchronized measurement technology (SMT) forms the foundation of Wampac systems, providing time-synchronized measurements of voltage and current phasors across the power system. The core component of SMT is the Phasor Measurement Unit (PMU), which measures voltage and current phasors with precise time synchronization provided by GPS signals. PMUs offer several advantages over traditional measurement systems: high sampling rates, typically 30 to 60 samples per second, precise time synchronization, microsecond accuracy, direct measurement of phase angles, real-time data transmission capabilities. Data concentrators (DCs) or phasor data concentrators (PDCs) aggregate data from multiple PMUs, aligning measurements to a common time reference and distributing the synchronized data to various applications. The IEEE C37118 standard defines the requirements for PMUs, ensuring interoperability between devices from different manufacturers. The implementation of SMT requires careful consideration of communication infrastructure, data management, and system integration. The high volume of data generated by PMUs necessitates efficient communication networks and data processing capabilities. Applications and benefits of SMT. Synchronized measurement technology enables both offline and online applications that significantly enhance power system operation and planning. Offline applications include post-disturbance analysis, reconstructing system behavior during events to understand root causes. Model validation and fine-tuning, comparing simulated responses with actual measurements to improve system models. Benchmarking, establishing performance baselines for system operation. Online applications include wide area phase angle and power flow monitoring, visualizing stress levels in the transmission system. Wide area frequency monitoring, tracking frequency dynamics across the system. Wide area voltage monitoring, assessing voltage stability conditions. Inter-area oscillation monitoring, detecting and analyzing low-frequency oscillations. Power system restoration, supporting system recovery after blackouts. Improved state estimation, enhancing the accuracy of system state estimates. Dynamic rating of overhead transmission lines, optimizing transmission capacity. Intelligent controlled islanding, implementing strategic system separation when necessary. Adaptive under-frequency load shedding, tailoring load shedding schemes to actual system conditions. These applications provide system operators with enhanced situational awareness and enable more informed decision-making during both normal and emergency conditions. Architecture of Wampac systems. A typical Wampac system consists of several hierarchical levels: measurement layer, PMUs installed at strategic locations throughout the power system. Data aggregation layer, data concentrators that collect and process PMU data. Application layer, software applications that analyze the data and provide insights. Control layer, control mechanisms that implement actions based on the analysis. Communication networks form the backbone of Wampac systems, enabling real-time data transmission between components. The choice of communication media, fiber optic, microwave, satellite, depends on factors such as bandwidth requirements, latency constraints, and reliability needs. The architecture of future Wampac systems in Great Britain is designed to address specific challenges of the GB power system, including the north-south power transfers, integration of renewable resources, and interconnections with neighboring systems. The implementation follows a phased approach, starting with basic monitoring applications and gradually expanding to include advanced control functions. Inter-area oscillations and monitoring. Inter-area oscillations are low-frequency electromechanical oscillations, typically 0.1 to 1 Hz, between groups of generators in different geographical areas. These oscillations can limit power transfer capability and, in severe cases, lead to system separation and blackouts. The physical nature of inter-area oscillations is characterized by coherent groups of generators oscillating against each other, weak interconnections between areas, high power transfers across weak interfaces, insufficient damping in the system. Monitoring inter-area oscillations requires synchronized measurements across wide geographical areas. The Newton-type algorithm NTA is an advanced technique for real-time estimation of oscillation parameters, including frequency, damping ratio, and mode shape. Compared to traditional methods like Prony analysis, NTA offers better performance in noisy environments and with time-varying signals. The Great Britain power system exhibits several inter-area oscillation modes, with the most critical being the oscillation between generators in Scotland and those in England. The integration of renewable resources and the changing generation mix can affect these oscillation modes, making continuous monitoring essential. Power electronic devices for damping. Power electronic devices play a crucial role in damping inter-area oscillations through their fast controllability. Three main types of devices are commonly used. High-voltage direct current HVDC systems. HVDC links can rapidly modulate power flow to counteract oscillations. Supplementary damping controllers can be added to the HVDC control system, using wide area measurements as input signals. Thyristor-controlled series capacitor TCSC provides fast control of line impedance, enabling modulation of power flow on critical transmission corridors. The damping control strategy involves adjusting the TCSC reactance in response to detected oscillations. Static VAR compensator SVC provides fast reactive power control, which can be used to influence voltage and power flow dynamics. Supplementary damping controllers can be added to the SVC voltage control loop. The design of damping controllers typically involves modal analysis to identify the most effective control locations and input signals. Residue-based methods are commonly used to determine the optimal controller parameters. The effectiveness of these devices depends on their location in the system, the availability of appropriate measurement signals, and the coordination with other control devices. Take an example of Great Britain. The Wide Area Monitoring and Control System WAMCS for the future Great Britain power system is designed to address specific challenges including renewable integration, north-south power transfers, and system stability. The implementation strategy follows a phased approach: short-term, deployment of PMUs at strategic locations, implementation of basic monitoring applications. Long-term, full Wampac implementation with advanced control functions. Key components of the GB WAMCS include PMU placement at critical substations, particularly at the Scotland-England boundary. Data concentrators for aggregating and processing PMU data. Wide area monitoring applications for oscillation detection and visualization. HVDC-based damping control for inter-area oscillations. The assessment of inter-area oscillations in the GB system reveals several critical modes that require monitoring and potential damping. The most significant oscillation mode involves generators in Scotland oscillating against those in England, with a frequency of approximately 0.4 Hz. Time delays in wide area control systems present a significant challenge, potentially degrading control performance or even causing instability. Mitigation strategies include delay compensation techniques and predictive control approaches. The research on Wampac systems has demonstrated their significant potential for enhancing power system stability and reliability. Key conclusions include: synchronized measurement technology provides unprecedented visibility into power system dynamics, enabling better monitoring and control. Inter-area oscillations can be effectively damped using power electronic devices with appropriate control strategies. The implementation of Wampac in the GB power system requires a phased approach, starting with monitoring applications and gradually expanding to include control functions. Time delays in communication networks present a significant challenge for wide area control, requiring careful consideration in system design. Future research directions include development of more advanced algorithms for oscillation detection and control. Integration of artificial intelligence and machine learning techniques. Enhanced cybersecurity measures for Wampac systems. Standardization of communication protocols and data formats. Development of cost-benefit analysis frameworks for Wampac implementation. As power systems continue to evolve with increasing renewable penetration and changing operational paradigms, Wampac systems will become increasingly essential for maintaining stability and reliability.